Hello, greetings from Sri Lanka. We are Team UOM from University of Moratuwa. We regret not being able to attend the final competition in person due to challenges we faced during the project development and unavailability of flights. As you might be aware, Sri Lanka is currently going through a major economic and political crisis. Therefore, we had to face delays in our PCB and component shipments, and we were unable to access the lab facilities freely because they were mostly closed due to the fuel shortage. Also, there have been power cuts during the day. Therefore, we mostly carried out testing at our home using the equipment we have. But still, everyone in the team tried their best until the last moment to finish the project. Unfortunately, we were not able to do that. But nevertheless, we are very thankful for this opportunity to present our project this way in a video. I will start with a brief overview of our design. Our inverter design was divided into two main sections as the boosting stage and the inverting stage. The design and implementations were carried out by two subgroups within the team. The purpose of the boosting stage was to step up the input voltage of 48 volt and 20 amp up to a voltage of 300 volt to 400 volt for the inverter. The inverting circuit will then convert the DC voltage into alternating and output a sine wave of 208 volt AC line voltage. Both circuits are controlled by a dual-core C2000 microcontroller. The design approach we plan to follow was to first test the boosting and the inverting circuits individually by gradually increasing the voltage and power, and then combine them to proceed with the testing for the rated specifications. So far, we have completely designed, manufactured, and tested the boosting circuit and the inverting circuit individually for low power levels. Also, we have completed the designs for the combined circuit. However, we could not get them manufactured due to the time constraints we experienced because of the delays in receiving shipments. First, I will explain how we did the implementation of the boosting circuit. As the first step, we defined the specifications and functions of the boosting circuit that we need. First, we would design it for low power levels close to 100 watt with the specifications in the first column of the table. The output voltage will be 300 volt with a minimum input voltage of 18 volt. The resonant frequency was specified as 68 kHz and a minimum gain of 14.3. In addition to the boosting, we decided to have galvanic isolation before the inverting circuit to make the transformer smaller, more affordable and efficient. The subgroup that was assigned for the boosting stage was further divided into two groups to evaluate two circuit topologies. The first was a phase-shifted full-bridge DC to DC converter. It had a center-tap full-wave rectifier with a full-bridge switching circuit. This switching circuit is controlled using peak current mode controller. During the testing, we could observe higher ripples in the output, which made it unstable. This is the PCB layout that we designed for this circuit and its 3D view. The transformer was hand-wound by us. In parallel, the other term tested the LLC resonance converter circuit. Different than the previous one, this circuit has a full bridge rectifier and the switching circuit is controlled using pulse frequency modulation. A stable output could be achieved by this circuit. Before the hardware implementation, we carried out a simulation on Plex for this LLC circuit according to this schematic. This was according to the specifications of the low power version of the circuit. Now let me show you the simulation results. The first two graphs show how the output voltage and the frequency varies with time. The green line is the reference output level we need to reach, and the red line shows how the actual output changes to reach that. As the frequency increases, the gain of the LLC circuit will decrease and become stable at the desired level. For a nominal voltage of 21 volt, we could observe that the output has reached the 300 volt level at the resonant frequency of 68 kHz. The figure on the right shows the voltage and the current waveforms of the LLC tank. The current has a sine shape as desired. This figure demonstrates the zero current switching and zero voltage switching in the MOSFET. This is the most important characteristic of the LLC circuit, which minimizes the switching losses. After verifying the circuit, we designed a PCB in the following way. This is the manufactured PCB and how it undergoes testing. The testing was conducted for these set of conditions. The input voltage will be varied between 21 to 29 volt, and the circuit will achieve a considerably stable output voltage of 300 volt. Now we are gradually increasing the input voltage. On the multimeter, you can see the output voltage of the LLC circuit. It only slightly varies around the 300 watt level. On the oscilloscope, you can see the PWM signals that are provided to the full bridge. They are varying in frequency. Now let's compare how the output voltage would change with and without the control system of pulse frequency modulation that changes the gain of the LLC tank as needed. In both cases, the input voltage is gradually increasing, but on the left-hand side, the LLC circuit is running with the controller, but on the right-hand side, it is being run without the controller. As you can see in the testing on the left-hand side, even though when the input voltage is increasing, the output voltage of the LLC circuit stays constant, but on the right-hand side, the output is increasing. Here are some important waveforms obtained during the testing. The top two transitions, which are the voltages of the midpoints of the half bridges, show a smooth voltage transition. And the bottom two waveforms, which are the gate signals of the MOSFETs in a half bridge, show a properly configured dead time as 100 nanoseconds. In this figure, we can observe how the transitions are being sharp square pulses at the resonant frequency compared to the other frequencies. We plotted the efficiency against time using the data collected during the testing. The graph on the left shows its simulated efficiency, while the one on the right shows the actual efficiency we obtained during the testing. As you can see, we could achieve a stable efficiency, close to 90% around the nominal input voltage. The second figure shows how the gain of the circuit varies with the frequency. The expected trend is for the gain to increase with decreasing input voltage and vice versa to maintain a constant output. This is achieved by varying the frequency according to this characteristic graph. The total gain is calculated by this equation where the gains of the bridge and the transformer is fixed. We could also identify the resonant frequency of 70 kHz and the minimum frequency of 50 Hz, which will provide the maximum gain possible using this graph. Now, to explain how we plan to upgrade the circuit to 1 kW. The PCB we have designed actually supports 1 kW power delivery. We only need to upgrade the transformer and the LLC tank according to this specification. Accordingly, we will customly design the transformer by ourselves, as it enables us to adjust and customize the transformer as we need. We have also considered using wide bandgap semiconductor devices for the full bridge. It will decrease the switching losses, but we have identified both advantages and disadvantages of high-frequency switching made possible by GaN devices. Therefore, we have included GaN in the final design, and we plan to evaluate the efficiency to determine whether it is suitable considering the higher cost. Now we will move on to the design of the inverting circuit, which was done alongside the LLC converter. The circuit topology that we chose was the 3-phase 2-level H bridge. This is controlled using space vector pulse width modulation technique, which is implemented on the C2000 microcontroller. The figure shows the measurements that we take using sensors and the control signals which are provided back to the circuit. By using this topology, we can easily disconnect one leg of the three-phase edge bridge and operate the inverter in single-phase mode. To test the proposed design technique, we first conducted a simulation on MATLAB Simulink. I will show you the results that we obtained. The total harmonic distortion at 1 kW was 0.09%. The power factor was 0.9945. The efficiency at 1 kW was 96.61 and at 500 watt 97.26. We simulated the active power delivery and the reactive power compensation according to the graphs provided in the request for proposal. In this, we could obtain results very close to the expected graphs. The above simulation was carried out in ideal conditions. Therefore, before initiating the hardware design, we carried out testing under low voltage conditions using individual modules such as edge bridge modules, current sensor modules, and voltage sensor modules. All of these circuits were designed by us. After verifying the circuit this way, we started designing an integrated PCB that combines all of these modules. According to the testing plan, we designed this PCB such that it is possible to upgrade it with minimal cost and within a shorter time. Therefore, we designed a baseboard that contains all the components that are common to all power levels, which are the sensing circuits and their power supplies as well as the control signals. The H-bridge circuit was the one that we upgraded along with the power. Therefore, it was designed to be pluggable to the baseboard. This is the layout of the baseboard that we designed. It is a 4-layer PCB designed considering signal integrity and power integrity with necessary clearance between the components. We had to go through 2 design iterations to end up with this final design. Here you can see the manufactured PCB and how the H-bridge card has been plugged into it while testing. Now I will show you the H-bridge cards that we have implemented so far. We actually designed and tested 3 versions of the H-bridge card that use silicon MOSFETs for these power levels. We also designed a card with gallium nitride FETs and digital isolators, which we could not get manufactured yet. Using the silicon H-bridge cards, we conducted testing up to 50 kHz switching frequency, 45 volt DC voltage, and 1.5 ampere current. Most of these tests were done in grid isolated mode using resistive loads. This slide shows our H-bridge cards. First one with optocouplers for low power. Second one with digital isolators for low power. And the third one with digital isolators for high power. All of these PCBs are 4-layer and have the same form factor that can be plugged into the same baseboard. This is the H-bridge card that we designed using gallium nitride FETs, which is the LMG3410 by Texas Instruments. This PCB also has the same form factor and has been designed according to the specifications provided in the datasheet. This is the 3D view. Using the H-bridge cards that we manufactured, we carried out testing under low voltage conditions. The controller of our inverter consists of a current control loop. The phase currents are first converted into the DQ frame, resulting in ID and IQ currents. They determine the active power and the reactive power respectively. They are maintained at the required level using 2 parallel PI controllers. In the final design, the required currents will be determined according to the grid voltage and frequency. However, as we were unable to test with the grid emulator, for the demonstration purposes, we will manually feed different reference currents and see how our inverter currents converge quickly to those levels. During the first test, the DC voltage is set to 12 volt. And we are gradually increasing the active current using the Code Composer Studio. You will be able to see that the power supply output current will increase. On the oscilloscope, you will be able to see the voltage waveform across the resistive load. This is the same test conducted for a DC voltage of 30 volt. These two graphs show the variation of the ID and IQ current with time. You can see how quickly they converge to their reference levels. To summarize, we could obtain a voltage waveform such as the one on the left across the resistive load and a current sensor output similar to the one on the right side. After verifying the boosting circuit and the inverter circuits for low power as shown earlier, we then designed a single integrated PCB combining them. During this integration, we designed the power supply circuits to provide the power to the components from the input source. In here, isolation between the circuit components of high power and those that interface with the microcontroller was considered. All of the MOSFETs were replaced with gallium nitride FETs to increase the efficiency and achieve higher frequency switching. The diagram on the right shows how the power distribution has been designed between different circuit topologies in the PCB. The chalk filter in the design has been hand-wound to reduce the costs. This is the layout of the 4-layer PCB which was designed according to recommended guidelines in the datasheets of the components. This is the 3D view. After designing the final PCB, we analyzed the cost of the design. We calculated this in two approaches. Both of them included the cost for bulk manufacturing. The first was done for the current implementation, which we have tested so far with silicon MOSFETs. Only the components that were available in stock was considered. Then we did the same for the final implementation that we plan to test next. This design has gallium nitride FETs and include components which are actively manufactured even though not in stock currently. We have left out the cost of the enclosure as we have not looked into its design yet. We are planning to continue the work and finish our inverter design with the resources we have even after the competition. As the next step, we are planning to get the final PCB manufactured while we are conducting tests for high power on the two separate circuits we already have. Then we are planning to move on to testing the inverter with the grid emulator and start debugging the final PCB. We are very thankful for offering us the opportunity to still present our project this way. We consider this as a huge encouragement and appreciation of the hard work of the whole team. Thank you very much.